Okay, so here's the derivation for an expression for the activity coefficients of a regular solution, where a regular solution entails that the average energy of the interactions between solvent A molecules and solute B molecules, between solvent molecules and between solute molecules are not the same. This is in contrast with an ideal solution where the average energy of these interactions are the same. So, just write that out real quick. Okay. So, essentially to get this expression, we want to start with the equation for a non-ideal solution or a real solution. The delta G of the mixture between A and B in a non-ideal solution is equal to nRT multiplied by the molar fraction of A times the natural log of the activity of A plus the molar fraction of B times the natural log of the activity of B. So notice that this activity term replaces the molar fraction in the ideal solution formula. This just means, or this is to reflect the fact that A, or the activity of A, is sort of an effective molar fraction, or how the fraction would be like in consideration of the fact that these A and B interactions aren't the same energy as these AA to BB interactions. So we have two formulas, this one being the first and this one being the second. So you could also express the delta G of a mixture of a real solution as nRT multiplied by the molar fraction of A, mole fraction of A multiplied by natural log of A of molar fraction of A plus molar fraction of B times the natural log of the molar fraction of B plus this lowercase xi term. So if I can write a xi, there you go. So this term sort of reflects the fact, or it reflects the fact that the average energy of these A and B interactions differ with respect to an ideal solution. So just a side note, if this xi is greater than or less than 0, these A and B interactions are more favorable than in an ideal solution, and this is an exothermic reaction. Conversely, if this xi term is greater than 0, it's endothermic, and these A and B interactions are unfavorable. So, just really quickly. So, what we want to do here now is that we want to introduce the equality that the activity of molecule A, or solvent A, is equal to this gamma A times the mole fraction of A, where the gamma A kind of just reflects the deviation from reality. So this is the activity coefficient, and this is what we want to relate to. This is kind of what we want to find, or we want to find an expression for this. So kind of just plug this into the first expression, and we get the following. Okay, and then we can kind of rearrange this using the identity that natural log of ln times AB is equal to ln A plus ln B. So essentially we want to split up this gamma and then this mole fraction term. So we're going to rewrite that using the above identity. And then this. Okay, so here we have our mole fraction terms on one side, and then our activity coefficient terms on the other side. So what we want to do here is we essentially want to compare the equation or the expression we just got with this one. I'm just gonna copy it over so it's easier to tell. Okay. Erase this. Okay. So here we can see that this clearly matches or maps with the mole fraction terms, but this does not. But we know that these two are equal, so we want to set this xi term of the second equation equal to the activity coefficient portion of the prior delta G equation. So in order to make these two equal, we want to sort of notice that the natural log of the activity coefficient of A must be equal to this xi term times the mole fraction of B squared. Similarly, the natural log of the activity coefficient of B is going to be equal to the xi term. It's a terrible xi, but whatever, times the mole fraction of A squared. So notice that the activity coefficient is the opposite of the mole fraction that we substitute with. So I'm just going to plug that in, substitute this natural log term, or these natural log terms. I'm just going to rewrite that to make it look better. Okay, so now what we want to do is we want to factor out this lowercase psi x plus, or mole fraction of A plus the mole fraction of B. So what we get is the thing we factored out, this lowercase psi term, and then we get the mole fraction of A times the mole fraction of B. So what you want to recognize is that the mole fraction of A plus the mole fraction of A plus the mole fraction of B is equal to 1. So this simplifies to lowercase psi xa xb, and you'll notice that the equality holds. So these expressions or equalities, the natural log of the activity of A is equal to xi, the mole fraction of B, the opposite component. So these equalities, these are called the Margulies equations. So at this point we kind of got to where we wanted to be, that is to derive an expression for the activity coefficients of a regular solution. So that would be this gamma term. If you want to go a step further, you can raise it to the power of E, and then you can get the activity of A is equal to E psi xb squared. Or if you know that x, or the mole fraction of B, is equal to 1 minus the mole fraction of A, you can even get it to E to the power of xi multiplied by 1 minus x A squared. Similarly, you can do the same thing for the activity coefficient of B. Is equal to E exponent raised to the xi lowercase I xa squared, so the opposite. Or you could just plug in 1 minus xb for xa and get the following expression. So here are your expressions to find the activity coefficient of a regular solution.